Is normal force always equal to force of gravity?
Problem 1. A 2-kilogram box is lying on the table. Mary is trying to lift the box with a string. She pulls the string with a force of 2 newtons, but the box does not move. Draw the free body diagram of the box and find the normal force acting on it. So first, we're going to write down our key ideas for this problem. And that is Newton's second law. Next, we're going to write down the information given to us in this problem. So that is the force of tension is equal to 2 newtons, and the mass of the box is 2 kilograms. Next, we're going to draw our free body diagram of the box. So we have the force of gravity pointing downwards, and force of tension, and force of normal. And since the box is not moving, the net force equals 0. Also, the upward y direction is positive, and then x is to the left, right. Next, we are going to solve for the normal force. So we're going to write our F net for the y direction. So we have Fn and Ft in the positive y direction, and then minus Fg since it's in the negative y direction, and equal to 0. So we can rearrange our variables to solve for what Fn will be. So Fn is equal to negative Ft plus Fg. Then we can plug in our unknowns. So negative 2 newtons for the tension plus 2 kilograms times 9.8 meters per second squared. So we get the final answer of 17.6 newtons as our normal force. Problem 2. A 2-kilogram box is lying on the table. There is a small hole on the table where a piece of string is attached to the bottom of the box. We pull down on the string by 6 newtons, but the box does not move. Draw the free body diagram and find the normal force. So similarly to the first problem, we are going to write down our key idea. And that is also Newton's second law. Then we are going to write down our given information, where the force of tension is 6 newtons, and our mass of the box is 2 kilograms. Then we are going to draw our free body diagram of the box. So we have force of tension and force of gravity pointing downwards, and the normal force pointing upward. Since the box is not moving, the F net is 0. And also, the upward direction is y, positive y, and to the right is positive x. Next, we are going to solve for our normal force. So we will write down the F net equation for the y direction. And we have Fn in the positive y direction, and Ft and Fg in the negative y direction. Then we can rearrange our variables to solve for what Fn is. So Fn is equal to Ft plus Fg. And then we can plug in our given information from the problem, where Ft is 6 newtons, and Fg is 2 kilograms multiplied by 9.8 meters per second squared. So then we find out that the normal force is equal to 25.6 newtons.
3. A 30-kilogram wooden box is lying on a wooden table. Sarah is pulling a rope with a force of 50 newtons on a 30-degree angle northwest. The coefficient of kinetic and static friction are 0.2 and 0.25 respectively. Draw the free body diagram and determine whether or not the box will move. If it moves, what is its acceleration? Okay, so first we start by figuring out what are the key ideas. That's the Newton's second law. And we should consider that F static max is equal to normal force times mu s. So then we are given that mass of the box is 30 kilograms. We also know that tension force is 50 newtons. We are also given that mu static is 0.25 and mu kinetic is 0.2. And we're asked to find acceleration if the box moves. So now we want to visualize this thing, which means that we want to draw the free body diagram. So the box is lying here. There's normal force going up. There's gravity that's pulling down. Here's the force of tension, which is making 30 degrees with the horizontal, and this is the force of friction that's making the trying to make the box stop. So we are making the axis y positive as it goes up, and x positive as it goes to the left. So now we want to solve this. Okay, so we write the F net x, which is tension force, the x component of the tension force, which is cosine theta, minus F friction, which is ma. But we don't know what our F friction is. We don't know if it's static or kinetic, so we need to figure that out using the F net in the y direction, which is F net y is equal to normal force plus y component of the tension force minus gravity, which is 0 because it's not moving either up or down. So we solve for F net here, which is Fg minus Ft sine theta, and Fn is Mg minus Ft sine 30 degrees. So if we plug the numbers here, we get that it's 30 kilograms times 9.8 meters per second squared minus 50 newtons times sine 30, which is approximately 269.3 newtons. Okay. So then we use this normal force to figure out what the maximum static friction is. So F static max is equal to normal force times mu static, which is in this case 269.3 newtons times 0.25, which is approximately 67.325 newtons. So we plug this maximum friction now in the F net x equation that we had above before. So here, okay, so we write the F net x. Now we're already knowing what's the friction force here. So it's F tension cosine 30 degrees minus 67.325 N, which is 50 newtons times cosine 30 minus 67.325 N, which is some negative number. We don't really need to know what the negative number is because the result that it is negative tells us that the friction force here is the static friction. So friction is static, and it does not reach its maximum. So the object does not move. So the acceleration here is 0.
Is it on, what color is it on now? It just started. Oh, okay. So we can cut the first part. Yeah. Problem 4, first part. An elevator is accelerating up by 15 meters per second squared. What is the normal force acting on the person with the mass of 60 kilograms in the elevator? Part 2. An elevator is in free fall. What is the normal force acting on the person with the mass of 60 kilograms in the elevator? So we'll start with the first part and the key idea. Is Newton's second law. And then we will draw the free body diagram of the person in the elevator. There are only two forces acting on the person. First one is the gravitational force, and the second one is the normal force. Because the elevator is accelerating upward, so we know that the net force is pointing up. And for this coordinate system, the upward direction is the positive y direction, and the positive x direction is to the right. So now we use the Newton's second law and solve for the normal force. So we know that F net equals the normal force minus gravitational force equals ma. And then we know that the acceleration is given, which is 15 meters second square. So F normal force equals Fg plus ma. And the gravitational force equals mg and we know that g is 9.8 meters per second square. So we plug in mass as 60 kilograms times the sum of g and a, which is 9.8 plus 15. And the answer we got is 1,488 newtons. So for the second part, our key idea is still Newton's second law. And we'll draw the free body diagram of the person now in free fall. We know that because of the person is in free fall, its acceleration is downward and it equals g. So we know that F net is downward. And our coordinate system is the same as the first part. So for this one, if we assume the normal force is in the positive y direction, then we have F net equals normal force minus gravitational force equals ma. And because the person is in free fall, we know that A equals negative g. So now we have normal force minus gravitational force equals negative mg. So normal force equals Fg minus mg. And we know that gravitational force is also mg. So we have a normal force of 0. So now, let me ask you this question again. Is normal force always equal to force of gravity?